The title of my project is Spatiotemporal Spectral Variability in Cassiopeia A. This research introduces a new method of astrophysical analysis using machine learning. The chosen case study is Cassiopeia A, called Cas-A for short. Cas-A is a supernova remnant in the constellation Cassiopeia and is the brightest extrasolar radio source in the sky. The supernova occurred approximately 11,000 light-years away in the Milky Way galaxy, and the expanding cloud of material left over from the supernova is roughly 10 light-years wide. Scientists study objects like Cas-A all the time in search of interesting regions. In our case, interesting regions are regions with abnormal color-light curves. Scientists sludge through mountains of data, literally hundreds of thousands of data points, to identify these interesting regions. Unfortunately, this takes time and lots of computing power. In my project, I developed an efficient algorithm to identify regions with statistically significant color-light curves over space and over time. In other words, I found spots on Cas-A that were interesting. But how, you ask? The algorithm I used was k-means clustering. K-means is a machine learning method of vector quantization and is popular for cluster analysis and data mining. K-means clustering aims to partition n observations into k clusters in which each observation belongs to the cluster with the nearest mean. In my project, the n observations were 8 X-ray images from the Chandra X-ray Observatory, and k clusters were interesting regions that I found on Cas-A. I used bins of 4, 8, 16, 32, and 64 to mask the pixels on Cas-A. The 5 bitmap images shown to the right show regions where pixel values were included in spatial and temporal variability calculations. For each pixel, I did the 4 following steps. First, I computed soft, medium, and hard bands for every pixel. I then generated color-light curves for each pixel using these bands, dividing soft by medium and medium by hard. Next, I flagged those areas of the remnant which showed an abnormal spectral signature based on color-light curves. Abnormal spectral signature was defined as pixels whose standard deviations were greater than 3 sigma from the mean. Finally, based on these pixels, I mapped out the regions on Cas-A that showed locations of abnormal behavior. Here are my results. The top set of images show the spatial analysis of Cas-A, and the bottom set of images showed the temporal analysis on Cas-A. The spectrally significant regions found at different binnings are noted by the red boxes overlaid onto the corresponding Cas-A image. As you can see, the k-means algorithm was able to pick up quite a few interesting regions on the remnant over space and time. This research introduces a powerful tool to model and predict the physical location of interesting regions on any astronomical object in an accurate and an efficient way. Scientists no longer have to sludge through mountains of data. They can simply run this algorithm and know where the interesting regions lie, saving time and effort thanks to the model and prediction of the algorithm. The impact of this research will help scientists do better work at a faster pace, ultimately expanding our knowledge of space, time, and our universe. The overarching implications of using machine learning in this field is an exciting first step into a world of problems yet to be discovered. Overall, this project was challenging yet very rewarding. I hope to inspire other young women interested in STEM fields through my work. Thank you for your time, and please feel free to reach out if you have any questions. I'd love to talk.